Hey guys, welcome for this session. So today our speaker for the session is Mr. Shantanu. I'll just give you a quick intro about him and then he can start with the session. So for today's webinar, Shantanu is going to take a 90-minute session on language models in NLP. Shantanu is the head of artificial intelligence products at inFeedo. He is an ex-member of Udacity's data team and alumnus of the flagship MIT Global Entrepreneurship Bootcamp and on the Alumni Advisory Board as well. Shantanu is a 12-time winner of the world's largest annual code competition, AI theme, and even an active contributor to the Stanford Scholar with one of its paper voted highest on the platform. He's a global speaker and guest lecturer at premier B schools in India. Shantanu has been a TEDx licensee in the past and currently advises multiple early-stage AI and edtech startups about revolutionizing education through AI. So I'll just ask Shantanu to now take over and start the session. All the best, guys. I'm sure you'll be making the most out of it. Shantanu, now you can start.
Awesome. Thanks a lot, Vijay. It was a great introduction.
Yeah.
And thanks to everyone, in
Yeah.
fact, for joining in on a Sunday morning, because I think it gets tough for a lot of people to join in and study on a Sunday morning. So thanks a lot for everyone joining in. A brief...
Shantanu, people will be if they have any query, they'll be sharing their queries via chat.
Right,
So
yeah,
you can have a look at the chat and just address that. Okay. Cool.
Yeah, in fact, so I was just going to address that. After every couple of slides, what I could do is I'll just give you a brief of the session, in fact, first. And it's basically going to be around, how language models are used in NLP. And of course, before I delve deep into language models, I'll give you a brief understanding of the use cases of where NLP is also applied in a couple of industries, how it can be applied, and what to do with the language models that you learn over here, basically. And I will have more focus. So the session is split into two, which would be the first one is the theoretical part of language models, where to use, how to use, what are language models, and so on. And the second is the code. So the code, of course, is something that I believe is very reproducible. And I would rather that most of the attention of all of the participants go into the first session, because it builds the base of what you're really learning. So code is basically you just knowing how to write code. And I think that's very accessible in the current day and age. So I think that's the crux of the entire session. If you have any questions related to the theory and everything that I will cover during the slides, please feel free to drop it in the chat window, and I will pick them up once every couple of slides. So as soon as I keep changing topics, I'll pick up questions from the chat that have been unaddressed. So I will begin the session now. So the session, as I said, is basically around language models, but a brief introduction to why we're doing language models particularly, and what natural language processing is all about. So it's basically, when we speak of, sorry, I think someone has problems hearing. If you could, are you the only one facing this problem, or?
Actually, it's pretty clear. I don't know if someone might face uh,
Okay, great.
I'll just type if everyone can hear.
Yeah.
Yeah, so they will reply.
Awesome, great.
Great. Go ahead. Cool. Yeah.
So the brief of what natural language processing is all about and why we use NLP before language models ideally is so when we speak of the field of artificial intelligence of sorts, and there's a lot of buzz around what AI is and what AI can do or cannot do, and there's something I think is a great thing to know about is if you see a lot of computer vision application these days, because AI is divided into a couple of subfields or sub verticals, so there's a lot of AI that does computer vision, there's speech, there's language, there's audio, there's a lot, yeah, there's a lot of other verticals of artificial intelligence. But what my personal belief is that natural language processing is something that will, so if you imagine a human, and if you've seen a lot of robots in say a lot of expos. There was a recent robot that came out that could talk to humans, and even Alexa and all of these things that come out as virtual assistants. What you will see is that a lot of AI will move forward, but they will hit a glass ceiling. They will hit a place where they can't move forward anymore, because the trait of being, close to human or performing human-like tasks is that you can speak to humans well. You can understand what humans are trying to say well. So that is the core idea behind natural language processing, is to give computers the ability to, understand and process human language. And I think that's the core of what artificial intelligence will need to grow at the scale that it's being poised to grow at. And there are three examples of where NLP is greatly used. And as you can see, there's something called a dialogue system. And if a lot of you have used Cleverbot, you will see that a Cleverbot is basically, it's a online application where you can talk to a bot. It gives you answers and all. So it's basically a conversation that a bot is having with you. Machine translation is again something similar, which is, if you type, if you use Google Translate, I think that's the core of machine translation. And question answering is a great feature that's in fact been introduced to Google search engines these days. So if you type who is the president of India on Google search, it'll also give you some related questions that you can click on, and you'll see brief answers at. So basically how you type a question and it finds the answer for you in the kind of corpus or text that it has is question answering. Yeah. So the next is what natural language processing does require is a great deal of knowledge of language. And some of the important questions that natural language processing addresses is this string, a part of this language? Is this sentence, is this phrase a part of this language or not? And I think how you would, in fact, even if you look at a lot of profiles of a lot of researchers in the AI space of things, you will see that NLP has a little harder of an entry barrier than a lot of other fields of artificial intelligence. So, for example, a lot of people say that you need to know a great deal of math and a great deal of computer science to be able to do good AI. And while that is strongly believed, computer vision, on the other hand, if we compare to natural language processing, you will see that computer vision requires a lot of edge detection, mathematics, and stuff, and you will have to have a great command over the code that you write algorithmically. In fact, in the case of natural language processing, you will see that you will also have to have a great deal of math and computer science understanding. But on top of that, you will have to have great understanding of the language that you're building NLP in. So a lot of linguists become great natural language processing researchers or workers, because they have a great understanding of how the English language works. The grammar, the past trees, everything. So you have to have intricate knowledge of language sometimes. But what we'll cover in this does not require a depth of how language functions, but just the base of what we've done in till our probably fourth grade, fifth grade is more than enough. So I'll dive into language models. And so that was a brief of what natural language processing is all about. And if there's any questions up until now, I'd love to take them up in the chat. Before I also delve into language models, I'll give you a brief of where natural language processing can be used and how it can be used in a couple of industries, for example. So I'm at inFeedo, and what we do is AI in HR, basically. And if you compare startups or schools, for example, they are into the field of education. So how language can be used in both of these contexts is that you could imagine all of you have been in junior school before, so fourth or fifth grade or sixth grade, where a lot of assignments that the teachers used to give you are very lengthy assignments sometimes, that you need to write and elaborate in long paragraphs, and then you give it to the teacher so that the teacher is able to check them. Or even the final exams that you give take a lot of time to come back from checking. And if they are just theoretical long answers, a lot of natural language processing can be applied in this space, so that assignments for teachers can be checked a lot faster, students get their results faster, and even detailed feedback on how their answer could have been made better. Maybe the grammar was wrong, maybe the contextualization of the answer was a little wrong. So computers in that space can help fast track assignment correction, and make it a lot better than it currently is. In the space of AI and HR is what I do on a day-to-day basis. Is if you guys are working professionals or if you guys are students, you'll find that one of the key problems that even students in universities have or employees in organizations have is that sometimes when I want to voice my concerns, I am not too sure if I'm heard, or I'm not too sure if my feedback is being accounted for. So if I have an organization of say 10,000 people, or if I have a university of 5,000 people, now if I do a quick survey poll on feedback, for example, on how my transport facilities are, I'll get 5,000 responses, 4,000 responses, and it's very hard for me to get a trend out of those responses. And I can't read through 4,000 responses or even remember any one of them. So then natural language processing comes into play there, where I get larger themes of what's been said, organizational context, if people are having more problems in a particular geography and maybe not in the other geography. So this is where NLP can be used to save a lot of time for someone who's using natural language. And I'll dive into language models now. So natural language processing has a couple of ways that you can use. So language models is basically some sort of an algorithmic or a probabilistic approach to understand the questions that we were trying to ask before. So if you see here, one of the important information what we were trying to get through NLP is this string a valid member of a language or not? And if we go to, say what defining what language models now are, these are probabilities that you get out of a model that gives you if the next word is useful in this current context or not. So for example, if I'm talking about my dog and I say my dog is name of the dog. So my dog is Spot, my dog is Jack. So if the word is a current fit to the previous three words, is what language models will give you sometimes. And if I'm using a wrong sentence, it will flag it because it will have low probability of that sort. And always, as you can see, the probability of all sentences being generated through this language model will have to sum to 1. I'll give you a great example of where language models are used. And as I defined before in the my dog is hyphen kind of a sentence, if you've seen speech recognition, I ate a cherry is a more likely sentence than I ate a jerry. So as you can see, this one has correct English language words, but the probability of these occurring together is something that is extremely low. OCR and handwriting recognition also uses a lot of language models because OCR is basically optical character recognition, where a lot of places you would have seen and a lot of applications, in fact, the Office Lens application is doing this a lot these days, is that if you write something on a piece of paper and you take a picture of it, you will be able to understand what, you can digitally get the handwriting of what you've written onto your phone. And that is optical character recognition. Machine translation, and this is something that we will delve into, some sort of machine translation we will delve into right now, is more likely sentences are probably better translations. And we can apply machine translation to a lot of things. We can apply it to part of speech tagging, which I'll delve into later. And the mechanism usually remains similar. Machine translation, again, is my name is Shantanu, could be converted to Hindi as Mera Naam Shantanu hai, and so on. And if we convert this to different languages, the exact probability of that sentence being generated will be a lot higher than some other sentence being generated in a similar language. Natural language generation, in fact, uses a great deal of language models. And this is a space in NLP that is lagging far behind than the other spaces of processing. And it's only because when we're trying to generate or when we're trying to create language, we have to make sure that we get absolutely high accuracies, because even one word or one grammar off will tarnish the reputation of a brand that's using natural language generation. Because I'll give you a great example on why NLG, which is natural language generation, is not used as much in the industry. Is because if I say, for example, you come to Google and you find that, the Google Assistant is trying to talk to you. You say, okay, Google. And the Google Assistant replies in incorrect grammar or incorrect, usage of language. You will think that Google's doing a bad job at whatever it's doing, and you'll move on, because the expectation from artificial intelligence and bots today is extremely high. And even if you miss that by a mark, the reputation of your brand gets tarnished quite a bit, because you'll tell 10 of your friends that, why don't you try this? The Google Assistant replies incorrectly, and so on. So that tarnishes the reputation of my brand quite a bit. Context sensitive spelling corrections. So this is again using a lot of probabilistic models to see that the word here, the starting word that is there, will be THERE rather than THEIR. And this is how a lot of spelling correction even works in the Google autocorrect. Any questions on a couple of these slides before I'd love to take them up? Awesome. So, as I said before, a lot of you have predictive text on your phones. And a language model is great in supporting predictive completion of sentences, because and this is the usage of something I will cover later, which is called n-grams. And if I write, say, for example, please turn off your cell, the most likely word in my database or in my corpus, which means a lot of people have used this sentence before. So the likelihood of the blank being filled with phone is a lot higher than the blank being filled with car, because please turn off your cell car will be using all correct English words. And, if I put please turn off your cell phone, it's also using the same correct English words. But the probability of phone preceding cell, and that probability is a lot higher than a car coming right after cell. And your program does not work, your program does not run, might be something of a similar sort that fills in the blank, rather than your program does not purchase or something like that. And as the bottom pointer says as well, it can guess what you're typing and give choices on how to complete it, because the way that you've typed and the way you've used these words before, completion prediction or natural language processing systems will have an idea of what word you will use after what word. So before I delve into part of speech tagging, I see there's a question on the chat. Can you give more examples of natural language generation and how it's different from machine learning? So ideally, the way I want you to see machine learning and deep learning these are tools of performing certain tasks. So if I say I'm doing a deep learning task in natural language, I can also do deep learning tasks in computer vision. So deep learning and machine learning usually in common, machine learning is more prediction of an output using a couple of input parameters and stuff like that. And all of these will fall into certain buckets of both machine learning and deep learning. These are fields and these are distinct verticals of artificial intelligence. For example, if you're trying to predict, as you can see, the iPhone X is doing a lot of prediction on whose face this is. So you can do that even using deep learning. You can do that using machine learning. Deep learning is basically, if I have to simplify it a lot, would mean, there are deeper, if you understand how neural networks work, there are deeper layers to prediction. And a great example that I got on how to specify deep learning is you are adding more features to a certain, say, object to give me a better prediction of what I'm trying to get. And a great example that I got back in uni for this was that if you're trying to predict what the mileage of a car is, let's imagine, I'll give you an example of how this could be both a machine learning and a deep learning problem. So if I'm trying to understand what the mileage of my car is, I will give it a couple of features, and those features will be, say, I give you the size of my car, I give you the weight of my car, I give you what kind of tires it has, and I give you what kind of make it has, and the engine it has, and maybe the color of my car. And a lot of people will think that, because when I heard this example, a lot of people will think, why is color an important predictor of mileage? But a great insight to note is, and I heard this when I was listening to this example, was that if the color of the car is dark and it's summers, the car will absorb a lot more heat, which will make the engine hotter and the mileage lower. So color has been a great predictor of car mileage a lot of times. And so I think if I give these 5 features, to predict the mileage of a car, I'll be able to predict it with some kind of accuracy. And I would call this some sort of a machine learning problem. Now, if I separate it into different, units, say, for example, I will give you these couple of features. I also want you to predict, say, the mileage of the car, how fast the car is going to go, and 3, 4 other things with distinct different probabilities that you could call some sort of a sort of a machine, a deep learning problem. Because why it's deeper is because it's taking a lot more features, it's taking a lot more inputs, giving a lot more outputs, and so on. So the deeper your prediction gets, or the deeper your input features get, by deeper I mean more detailed, that becomes a deep learning problem, and this becomes a machine learning problem. Natural language generation can both be explored in machine learning and deep learning. So I would want you to think of deep learning and machine learning as tools to do something. Natural language generation is a field of doing something. And I hope that answers your question. If there's something on a follow-up, you can please drop it on the chat. Okay, so I'll move on to part of speech tagging. And so this is a great example and an important use case for language models to tag speeches or to tag languages based on their part of speech, because this is a huge area of some sort of industry application that we do. And a lot of times this helps in both, as you saw in the previous examples before. Please turn off your cell phone, or please turn off your cell run. You'll see that a noun is more probable here, which is phone, and run is like a verb. So I think a lot of spaces of natural language prediction will use part of speech tagging as a base of language models. And I'll dive deep into this in the theory as well as the code that we're trying to follow. Will basically be how to build a language model and solve for part of speech tagging. And part of speech tagging, as you'd all know, is, there's a lot of parts of speech of the English language. Say, there's nouns, there's verbs, and there's adjunctions, and so on and so forth. I'm not well aware of how many parts of speech there are, but I'm pretty sure there's about 20, 15 to 20, or a lot more of them. So I think the two sentences that we'll first delve into is Mary saw Jane and Jane saw Will. So here, let's try to understand how many nouns we have and how many verbs we have. And as you can see, Mary has been used as a noun, saw has been used as a verb twice, Jane has been used as a noun twice, Will has been used as a noun once. So when we have an understanding of how many times a word has been used, and if you have a fair understanding of machine learning, and this is a part of supervised learning and machine learning, would be that you have labels to your data, and then you train your probabilistic or statistical model on your labeled data to give you better prediction and outputs on your unlabeled data, is machine learning. So this will look a little similar. And this is called, we're trying to understand if Mary has been used as a noun a lot more times or a verb a lot more times. So right now, if I get a new sentence saying Mary saw. So saw could be, a verb or a noun or whichever. But in this case, if I write a Mary saw, I will get a noun, verb, and verb, which might be incorrect. And in this case, what this way of part of speech tagging is called the most frequent class tagger, which means the MFC. I'll just write that down for you. Just a sec. So the MFC is called the most frequent class tagger, wherein if I have a sentence that says, Mary saw Mary. In this case, I will correctly tag my sentence as noun, verb, and noun. Because I see that Mary in my table has been used as a noun a lot more times than the verb. Saw has been used as a verb, and Mary has been used as a noun again. But if I do something like a Mary saw, as I said, I'll get a noun, a verb, and a verb, which will be very hard to interpret and even quite incorrect. So moving on, I hope everybody is clear with how the most frequent class tagger is working in this case. Yep. So, as I had spoken of before, the dilemma in most frequent class tagging, in part of speech tagging, is that if I have two sentences, Mary will see Jane and Jane will see Will, we see that Mary has been used as a noun most, see has been used both as a verb, Will both as a verb, once as a noun, and Jane twice as a noun and 0 times as a verb. So if I see Mary will see Will, what do you think the new sentence will be tagged like? So if I write here, Mary will be a noun. If I go to will to see, it will be tagged as a verb, which is correct. See will be tagged as a verb. The last word that I come to, which is will be tagged as a verb again. And this gives me an incorrect part of speech tagging, which will probably later come back to me and tell me that, this is not how part of speech tagging should have worked. Will is a person that you're tagging and not somebody who's, a verb and something like that. Just a second, I think my mouse pointer is. Just a second. Yep. So, as you see, this is one of the greatest dilemmas of part of speech tagging's most frequent class tagger in probabilistic models, because it will tell me that will has almost double the probability of being tagged as a verb rather than as a noun. And that will skew a lot of my part of speech tagging. So how do we solve this sort of a scenario? And which is where I'll delve into something called the n-grams. Now, what we've been currently doing are called unigrams. Unigrams are basically uni standing for one, and gram is standing for a part of a sentence, which in this case will be a word. So in the bigrams approach, what we can solve for is now we'll try to see which word is associated with which word in my sentence. And we'll see here that Mary and Will is a noun-verb combination. And Mary Will has been used as a noun-verb once. Will see has been used as a verb-verb, and it's been used as a verb-verb twice. Mary Will has not been used as a verb-noun. See Jane has been used as a noun-verb, a verb-noun, and it's tagged here. A Jane Will is tagged as a noun-verb, and so on and so forth. So when you get a new sentence now, and we try to use the bigrams approach, we see that Mary Will is tagged as a noun verb. So we write noun here and a verb here on this will. Will see is used as a verb verb, and see will is used as a verb noun. So now all of our tagging will be correctly completed if we use the bigrams approach. And there are two problems, and then you must note that I've been pretty unclear and ambiguous with how we solve this problem of the bigrams. And once I see there's a question, let me just take that question up right now, because I think a lot of confusions will come up later. See always precedes a noun, and will has been used as a noun once. So won't this make will in the new sentence a noun? See precedes a noun. Just a sec. Yep. So this does make will a new sentence. So I don't get the question quite accurately. So won't this make will in the new sentence? So are you talking about the second will, or are you talking about the fourth will? So yeah, the last one is correctly attributed to a noun. So if you split this into bigrams, and bigrams are a combination of two words. The first bigram is Mary Will, the second bigram is Will see, and the third bigram is See Will. So if you search for Mary Will in your table, you will find it's tagged as a noun verb. So you write noun at Mary, will with verb. The next is a will see, which is a verb verb. So there's already a verb tagged on will. And you write a verb on see as well. And the next bigram is see will, which is a noun verb, a verb noun. Who decides that will in C will is a noun, and who decides that will in Mary will is a verb? Who does this tagging? Is there a dictionary? So yeah, so as I said, in fact, when I'm speaking about label data, the first two sentences that you see are currently the data that we have, which means the table that you see created is a table that we will create ourselves. And we will have some tags initially that a lot of, so this is something that natural language processing has as, as a huge blocker in the space, is that a lot of linguistics and a lot of linguists will have to manually create this table initially. And yes, as you see, there's no dictionary of sorts. But if I have about thousands of sentences, the first 1,000 will be tagged by linguists and humans sitting right there and making this table. Once this table is created, the new sentence will be tagged based on this table that I already have. And I hope the previous question is cleared of won't this make will in the new sentence a noun? This is making will in the new sentence a noun, because if you see the last bigram is see will, and our last bigram in our sentence is see will as well. The tagging for see will is a verb noun. And the most frequent class in the see will bigram is a verb noun, which means the see will be tagged as a verb and will be tagged as a noun. Yep. And the second question is NER similar to part of speech tagging? So just to elaborate on this question for a lot of others who might not know what NER and POS tagging are, NER is something called a named entity recognition, where if I say, if I write Mary, the system should tell me that this is a person. And if I write time, it should tell me it's, if I write basically 12 o'clock, 1 o'clock, 2 o'clock, the system should tell me this is time. Part of speech tagging, although, is Mary will be a noun, 12 o'clock, 1 o'clock will be another part of speech. A will be a verb, see will be a verb, and so on. So this is part of speech tagging, where the English language parts of speech are used to tag sentences. Named entity recognition will build right on top of part of speech tagging accurately, is because now that I have 10,000 names, I will classify all of these names into NER, which is the names bucket. So I'll just take these three questions and then I'll move on in the interest of time. So if there are 10,000 sentences, then do we first need to make the table ourselves, or there's some software? Most times you will have to, so if you want higher accuracies, a lot of people usually end up building their own sentences. And if you've heard of something called the core NLP by Stanford, a lot of these guys employ people to just sit out there and make these tables for them. And that's what there's something in NLP called annotation and annotators. So you're just sitting there. If you want higher accuracies on your models, there are some softwares that will help you do it. But if you have 10,000 sentences, and if you want to create something very unique, you would rather have the 10,000 sentences created in the table yourself rather than giving it out somewhere else. So it's called, you're basically putting in effort for 10,000 sentences, but for the millions of sentences after that, you already have a probabilistic model doing this for you. What if the sentence is a 5-word sentence? Was this technique fail to correctly tag? So I will dive deep into both sparsity and I'll give you a brief answer to that problem. I will dive deeper into what you've just said. But if it is a 5-word sentence, that bigram will 5-word sentence, do you mean like 5 grams when n grams set to 5, or do you mean a 5-word sentence? The bigram technique will not fail based on the length of your sentence. It will fail if those 2 bigrams are also occurring in different classes. So I'll dive deeper into the question, because I believe the question is of sparsity of your bigrams and not the length of your sentence. So if your question is if the longer sentences fail using bigrams, I wouldn't say they fail because of length of a sentence. The last question I'll pick up is, what if the new sentence contains words not there in your training data? So as you see a pointer in the last of my slide as well, and I will be addressing that right now, is the problem in this case, if the new sentence was, Mary will see Jack. See Jack is an unknown n-gram, which means UNK n-gram in my slide even speaks about that. And I'll delve deeper into how to solve unknown n-grams. Is if we don't have that sentence, the bigram approach will not work as accurately. And I'll delve into how it won't work accurately. So, as you can see here, a brief summary of what we just spoke of, which are n-gram models. N-gram models can be over, a sequences of words, characters, syllables, or any other units that you want to build these on. And a lot of times, for extremely high accuracies, people build n-gram models, which are bigram models sometimes, over 2 letters. So if I go back to the slide, Mary, in this case, Mary, people will also, if you have a lot of training data, MA and RY will become one bigram. For example, MA follows RY or MA follows MA. That becomes different. So if someone's trying to say mother, they will say MA, MA. If someone's trying to say a name of somebody, they'll say MARY. So that's how deep and detailed bigrams can get sometimes. And what they're trying to do is they estimate the probability of each word given the prior context. So in this case, this is a Bayesian equation that says what is the probability of the word being a phone based on the past 5 words being please turn off your cell. And this is in fact an extremely high, this is a 6-gram model. If you see please turn off your cell phone, because it's using 6 words. A unigram, as you see, an n-gram model uses n-1 words of prior context. So a 6-gram model will use n-1, which is 5 words of prior context. And in the top, you see, please turn off your cell are the 5 words it uses to predict phone. And you'll see it's a lot more accurate the higher the number of your n-grams get. But it also gets quite sparse, because if I only have please turn off your cell phone in my data, and I have nothing else in the space of please turn off your cell, then it'll always give me phone. But sometimes if some other word is actually more probable, it won't show it up as much. And as you see, what unigrams are is probability of a phone occurring. A bigram is probability of phone occurring given that cell was used, and so on. So now I'll delve into what Markov assumptions is. And what a Markov assumption, on a brief note, and I don't want a lot of people fixating on this because I'll dive deeper into this in just the next slide, is a Markov assumption is basically we are assuming that the future behavior of some sort of a system that we create, a probabilistic model, depends on its recent history and not 10 times, 20 times before, 20 words before. Basically, if I make a 5th order Markov model, the next state depends on the 5 most recent states. And the same way, if you see an n-gram model, and if you see a trigram model, for example, the probability of phone occurring only depends on the 3-1, which is trigram, 3-1, the past 2 words, and not the past 500 words or 50 words and so on and so forth. It only depends on the order of the model, the probabilistic model. So now, since we had unknown words and we needed to solve for unknown words, a Markov model will be a great way to solve for these words, and I'll dive deeper into how we'll be able to solve for a lot of problems that the n-grams has in this case. So any questions on n-grams before I move on to Markov models? I will take them up right now. Okay, great. So since, yeah, I think, awesome. So what a hidden Markov model and why we call them hidden Markov models is because these are hidden layers, because these layers are not visible to us. What we see is the start and the end of a sentence, and we see the words between it. And a Markov model is, again, what we're trying to do is predict the probabilities based on the order of the Markov model. And if you see, if I have a sentence, for example, that says Mary will spot Jane, or Mary will spot Pat, for example. Now these sentences will be broken down into what parts of speech these words were into, and what the starting of the sentence was, and what the ending of the sentence was, and what parts of speech these words had, and so on and so forth. So basically what I will tell you in the next 2 slides will be what transition and emission probabilities are in using hidden Markov models. So this is one of the easiest and the best explanations to the hidden Markov models that I got. And they will help you get a great understanding of how language models work in probabilistic ways. Is how these sentences are generated. Is imagine yourself standing on the start of a sentence. and there is a certain probability to go to Mary. Now, if your sentence has, let me write and annotate a sentence here for you, so it's easier to follow through. Can everyone see the annotation? Yeah. So this is the sentence that we're trying to tag, which is Mary will spot Jane. And we need to understand what parts of speech these are, we have in this sentence. I've put an S tag here, which stands for the start of the sentence. I will put an E tag here, which means the end of the sentence. Now, if I move forward from my sentence, I will see that S is where I begin. So in the hidden Markov model, if you see you're standing at S and you want to move to Mary, the probability of you moving to Mary from start will be given by transition probabilities. And if a lot of you have done, graph analysis, or I think it's a topic in math and even in computer science subjects and automation theory, you will find that this graph looks very similar to you, which means if I want to transition from, say, the start to the first word, Mary, I will see the transition of a node from S to N. And when I see that, it accompanies with certain probabilities. So if I just try to write it down here, just a sec. Just one sec. Yeah. So if I try to move from start to Mary, it'll accompany certain probabilities from moving from the start to a noun state. That probability will then be multiplied by the probability of Mary being a noun, which will be called emission probabilities. So transition probabilities are the probability of a noun being followed by a modal being followed by a verb, and so on. And emission probabilities are probabilities of that word being associated to a modal, or that word being associated to a noun, and so on. So this might not be clear in start, but I think once I try to explain what transition and emission probabilities are, it'll be greater to understand how we can maneuver through this graph a lot easier. So in the two sentences that we had, let's try to create a table that will help us understand. And these are the sentences that we had. Mary will see Jane and Jane will see Will. The other sentence and the four new sentences will be, if you can see the screen, these are the four new sentences that we have that we'll use to create this table. So first we'll try to cover transition probabilities. In this case, now that you see we've tagged these, and this is the table that we were creating manually before as well. Mary Jane can see will be tagged as noun, noun, modal, verb, noun. And we'll obviously put start and end tags at the end of every sentence. Now, once we've created these, let's try to put them in a table. And we see that the start is accompanied by a noun 1, 2, 3 times. So we write a 3 here. The start is accompanied by a modal just once. So we write a 1 here. And in this entire row, we divide the row based on the number of probabilities of number of observations of the start tag, which in this case are 4. So we come up with 3 by 4 and 1 by 4, which are the probabilities of the start tag being a noun and the start tag being a modal. So there's 75% chance. And M is a modal. Will is a modal verb that we're trying to use here. Here, moving on, once we have these probabilities, we try to fill the noun. And the noun in this case, followed by a noun, will be once and just once, as I can see. And you guys can see using these tags as well on the right, that the noun is followed by a noun only once in these sentences. A noun is followed by a modal 1, 2, 3 times, and we write a 3 here. Noun is followed by a modal thrice, yeah. So now, a noun followed by a verb. I think this is written incorrectly. There should be a 3 here. And if you do a 3 by 9, you'll get a 1 by 3. A noun followed by a verb will be once, as you can see. So you write a 1. And a noun followed by an end tag, 1, 2, 3, 4. So in all cases, we're following the end tag after a noun. And that gives us a 4 by 9. A modal followed by a noun, just once, on the third sentence, and so on and so forth. So these will be basically the probabilities that tell you that what is the chance that a noun will be followed by a noun, and so on. And in this case, when you try to maneuver the graph, you will see that once you're at Mary and you find the word will. So is the probability of emission greater, or is the probability of transition greater? So the question on the chart is, what is 9? 9 is basically when you sum these entire row and you divide to get the chances of each noun being followed by which one. You're basically dividing your number of observation by the total number of observation to get the probability of each observation. And 9 is the total number of observations in the noun row. Emission probabilities, on the other hand, are what are the chances of my word being a noun, and what are the chances of my word being a modal, and so on. So will, in this case, as you see, has great high probabilities of being a modal and very less probabilities of being a noun. But you will see that the Markov model handles this beautifully because it also takes into account the transition probabilities and the emission probabilities both. So once you're moving through the graph, and I'll show you just for a sentence of, say, for example, let's pick one sentence here. Mary will pat Spot. I start at the start tag. My start tag to noun transition is 3 by 4. So I'll just annotate here for a sec. Yeah. So my first transition probability is a 3 by 4. A 3 by 4 with the probability of Mary being a noun, which I go back and see, is just is 4 by 9. So my first probability here becomes 3 by 4 into 4 by 9. Mary being followed by will be a noun to modal probability, which is 1 by 3 into 3 by 4. And will pat will be a modal verb, which is 3 by 4. Pat being a verb is 1 by 4. Vn will be 1 into pat. Spot being a noun is a 2 by 9. So I think this is a rough way of how we will multiply both transition probabilities and emission probabilities to get the probability of this entire sentence being generated in this part of speech. So now the problem would be that if I see, say, for example, a word which is both a noun and a verb, I see Spot being more of a noun rather than a verb. If I multiply here the probabilities of transition, which is Vn, 1, multiplied by 2 by 9, 1 into 2 by 9 will give me a 2 by 9. Although 1 into 1 by 4 will give me a 1 by 4. And now, when I try to see in the larger scheme of things what the probability of Mary will pat Spot, with Spot being a verb, and once you try to solve that using these two tables, you will see that the probability of the entire sentence being generated will be a lot lower than this particular one. So we will know that that is the more probable sentence to pick. And here, how the hidden Markov model solves for unknown words, which are also called out of vocabulary words, is we will train a model that includes an explicit symbol for an unknown word. And in this table, as you can see, the table that we've created, we will create a word called UNK and store it into our table. And we will replace the first occurrence of each word of this data with UNK. So every time a word that we don't have will be replaced by the word U and K in our data. I think before we delve into model combination, I think Markov models as a larger scheme of things has been quite tough to explain and understand both. So if there's any questions on Markov models, I'd love to take them up now. Once we solve it through the code, we'll also be seeing that it's a lot easier to go through the code and understand what's really happening. Okay, great. So now what happens is when we have, as you can see, as n increases, if I go back to my slide of n-gram word models, I see that a unigram or a probability of a phone being a word in this current space of things might not be as high in isolation. But if I use a 6-gram approach, which will be please turn off your cell phone, I'll be able to get the probability of a phone being accurately in place over here rather than just in isolation. So as n increases, if you go to 6-gram, 7-gram, 10-gram, the expressiveness of the model increases. You'll be able to predict better, a lot better. But the ability to estimate accurately also decreases because your data gets sparse. And by the fact that your data gets sparse, you'll have a lot of zeros in your table. And that will always keep giving just one class, and it won't be probabilistic of sorts. And a great approach that's been used in the industry to combine n-gram models of increasing complexity is basically if I use a 4-gram model alongside a 2-gram model and so on and so forth. So just combining these models. So the error of one model is replaced by the other model working out in that case. And just a brief touch up on probabilistic models and language models of sort is language models assign probabilities to these sentences and these words being, a legal string in a language or not. And as you saw in parts of speech, we'll be able to tell if noun, verb, noun is a better combination than noun, noun, noun in a lot of cases. And they're extremely useful as a component of many natural language systems. And, as you saw, that simple n-gram models are easy to train, but sometimes when the n is smaller, they aren't as strong as larger n models. And once you keep increasing the n, the expressiveness of your model keeps going higher and higher. And although n-grams do give inaccurate parameters, because if we train them on a lot of zeros, they'll keep giving us one particular size of outputs and so on. So we will have to combine a couple of n-gram models to tackle sparsity in our data. So now I'll dive into coding a hidden Markov model on Python. So if there's any questions on Markov models before, I'd love to take them up now. Great. So I'll just set up the code walkthrough for this session. So while I do that, I'll just take a minute. Please feel free to drop any questions on the chat. I'll take them up in just 2 minutes. So the question on the chat, So Markov models are basis of neural networks. Neural networks are a different kind of an algorithm, and it would be unfair to say that they're similar of sorts, but Markov models are transitioning. So Markov models are basically, if you've been a computer science major of sorts, these are graph traversal problems, so these are nodes. Markov models create nodes, and these nodes are then traversed. So once you traverse from one node to the other, what are the chances of this node being followed by this node? And what are the chances that this word belongs to this node, are what Markov models do. Neural networks, on the other hand, have prediction functions in them, and they have backpropagation involved. So that's trying to solve a completely different way of tagging, part of speech tagging, and this is something that's a little different. So the second is, can you suggest some resources to learn about Markov models in a more intuitive way? I will drop the presentations and the code both for you to take a look at. But a great way to learn about Markov models and probabilistic models is I have a great friend who goes by the name of Luis Serrano, and I think he's now a machine learning instructor at Apple. So I would love if you could check out some of his YouTube videos, and I think he's got some wonderful, wonderful explanations on Markov models. And I will just drop the name out on the chat for you so you can. Yep. So you can check out Luis Serrano's YouTube videos, and I think that's a great way to start with Markov models. Is Markov assumption realistic? I am not too sure about the question. I mean, it looks pretty realistic to me, so I don't think it's a probabilistic model. So I'm not too sure what the question is. We have probabilities on each sentence being generated in a particular way, and the highest probability sentence gets the tags that it's generated. So I would say it's pretty realistic of sorts. How is the industry usage of Markov model as compared to the RNNs? RNNs are sequence-based models, and Markov models are decently similar to what RNNs cover. But I would say that RNNs are a lot more used in the industry than Markov models, only for two reasons. Because the industry is heavily, it's more performance-oriented, and the industry is more accessibility-oriented. So an RNN today is a lot easier to code down than a hidden Markov model. But a great way of understanding RNNs are understanding Markov models, because there's so many units and there's so many LSTM units, GRU, gated units inside an RNN. So that is extremely, deep maths that you're getting into in the industry. So if you have a fair understanding of how transitioning probabilities work and Markov models work, it'll be easier for you to code down RNNs in the industry. So I think the next 2-3 questions will be the last ones that I pick up before I begin to code it down. In what scenarios should we consider the usage of Markov models? Part of speech taggings is a great place to start with Markov models. And I think it's been used widely, extremely only in the part of speech tagging space. So this is a great scenario to use Markov models. I have address as a long string and want to split it into something, recipient, address line, city, state. In fact, definitely, this is something that can be, quite well solved by Markov models. Because if you split it into recipient, address line, city, state, you'll see that those recipients have a particular address, those addresses have a particular city and a state, and the probability of that similar. So a great example of how this will be solved by Markov models is that you'll see that Mahatma Gandhi Road or MG Road is almost in every city in our country. So if we have a recipient, we have an address line and the city and a state, it'll be easier to bucket which MG road this is. Is it Delhi? Is it Mumbai? Is it Kolkata? Which MG road is this? So I think this is a great problem to solve using Markov models. Does this part of graph theory used in self-driving? Yeah, this is a part of graph theory. This could be called a part of graph theory. I'm not too sure about motion planning of sorts, because so I think another note on the artificial intelligence space of things is that the space of things of AI is extremely large. So when you say that, natural language processing tool, so if you learn something in the NLP space of things, it doesn't necessarily mean you will be able to solve something in particular using that in the computer vision space of things or the self-driving car motion planning space of things. So Markov models do create a lot of the graph theory. This is a huge part of graph theory. I'm not too sure how they could be used in self-driving cars. So the last question I'll take up before I move on is, does Markov model work for numerical data? if you have to deduce textual data from numerical data. Could you give me an example of how you would deduce textual from numerical data? So if you have like prices, sale prices, do you mean like if you have greater than $100 is called cheap, expensive? I mean, could you elaborate a little bit on your? Oh yeah, yeah. So if that's what you mean, then Markov models can be used for that aspect. Great. So I think I'll move on with the code walkthrough of how to code down part of speech models. Yeah. So as you can read the introduction, and part of speech tagging is something that we're trying to understand the category of a word from the word surrounding its context. And as you can see, this will also depend upon the n-gram as we set at whatever gram that we set the n-grams at. And this is extremely important to have computers understand language in a lot better way. So that, you know, as you can see the example here, is discount as a noun versus discount as a verb. And this is extremely useful in information retrieval. So if I'm trying to tell one of my voice assistants, so, you know, can you call water? Water may be the name of a person, water may be the name of a store, or water may be just water that I want to drink. So it might be a lot varied, and this is very helpful in information retrieval. So a pomegranate library is a Python library that is used to build hidden Markov models. And we'll be using the pomegranate library to build hidden Markov models in this case. And as you can see, HMMs have been able to achieve extremely high accuracy with larger tag sets on realistic text corpus. And they've been used in a lot of other spaces, as you see, that speech recognition and speech generation, machine translation, these are the examples that I already gave before. They're also used in OCR with human gesture recognition and so on. So this is the example of what we saw before as hidden Markov models. So the first cell that we'll run with, and as you can see in the display above, that this is a sentence that we're trying to tag, and we'll be able to tag, in this case, will is a noun, the other will is a verb, and so on and so forth. So these are transition probabilities. The probability of a noun following a verb following a verb, and so on. The word will being a noun is called the emission probability. So here, we'll start by running the first cell, is the auto reload cells, which means that if sometimes the kernel dies for you, these libraries will import themselves automatically. Here, we'll import the couple of libraries that we need. The standard ones that a lot of you have used before, which is numerical Python, matrix plotting libraries, and collections, and so on and so forth. The new library that we will import in this case would be pomegranate. And pomegranate is a great library to use to, you know, build hidden Markov models and distributions. So we'll start with reading in a text corpus, and we'll split it into training and testing sets. So this data is used from the Brown corpus, which is, if you guys have used the NLTK library in Python, which is the Natural Language Toolkit. And this library has something called a Brown corpus, which is from the university. And this has been pre-processed to include the universal tag set. And the universal tag set, if you see, are only, say, the top 15, 20, 12 tags. I'm not sure how many tags, but these are the universal tags. So, for example, nouns and verbs. And they don't dive into which type of verbs and which type of nouns, proper nouns, and so on. So this just says noun. And this is why it's called the universal tag set. And you will get, of course, higher accuracy if you use the full, pen tree bank tag set, which means the 50, 55 other English language tags. But the process, as the code says, will be very similar. So once we run this, we're trying to load in our data using the dataset function. We'll first get the universal tags from this text file and the Brown universal corpus from the Brown universal.txt. We will split the training and testing into 80-70. You can maybe change it 80-20, so you can maybe change it to 70-30. And I'll share all of these files with you, so it'll be easier for you to run through the code as well. So once I split this into 70-30, you see this is a split that we create. And now, once we load in the data, we'll see that the data has a key value pair because it's been created in some sort of a dictionary format. And each of these sentences is keyed to a unique sentence identifier. So these are some sorts of keys that you will see. And if I type that key, what I'm trying to do is I'll get the sentence that that key belongs to. This is the sentence. And these are the tags of that same sentence. And this is my labeled data. So this is all of the data that I already have labeled, which means hopeful is an adjective here, and say traditional is a noun here, and so on and so forth. This is already labeled for me. And this is the labeled data we were speaking of earlier, that we will have to create these tables manually, and someone's already labeled this for us. So it'll be a lot easier for us to go forward with this. If you change the key, you can see that there are some different sentences that keep coming up. Now, the next step would be, as we saw before, we need to count the total number of unique words in our data to be able to create that table for us. And as we see these are the total number of samples of 56,000 unique words in our corpus. And these are the unknown words, as you see. There are 8,500 words that are missing in the training set. And you might want to go back and change the split and maybe see how this number changes or functions. So if we go back up and change this to 75, we'll see that this changes. So it's very natural that the more training data that we have, the lesser unknowns we'll have in the test set. But the objective of this is not to reduce the number of unknown words in our test set. So once we have these numbers, and right now all we've done is count words and just try to load in our data. So nothing that we've done in the processing space of things yet. Now we'll see how to access words and tag sequences. So the dataset function that we saw, that the data that we've loaded, the dataset has two columns. The first, as you see, is X. The second is Y, which means for each sentence, how the data is structured is the data.x contains the sentence, the data.y contains all of the labels that we have for that sentence. So in this case, you can see Mr. Podger had thanked him and so on. It's already tagged noun, noun, verb, verb, pronoun. So our data set is structured into sentence label, and so on and so forth. Now, how we'll access these word tags is something that we saw here. And now moving on, we can use a function called dataset.stream, word comma tag for the entire corpus. And once we move on, we enumerate data.stream. And what data.stream is doing is it's giving out word tag pairs. And we'll stop at 5 here, but if you want, you can change this number to maybe 8 and see how different words are coming out in the data.stream way, in a way that each word has an associated tag paired with it. And this becomes one unit. So for both the baseline tagger and the HMM model we'll build, we will actually have to estimate the frequency of these tags from the frequency count of observations. And that is similar to what we were doing in the previous table that we built. So the baseline tagger and the HMM model are different in the space of things that the baseline tagger is the most frequent class tagger, which will mean that, say for example, thanked has been used as a verb maximum times. So every time thanked comes in our new sentence, it'll be called a verb. So the simplest tagger and a great baseline for tagger performance is to choose the tag that is most frequently assigned in any sentence. And the MFC that we saw in the earlier presentation as well worked pretty well for us, but only broke out in a couple of sentences. So we've created here a function called paired_counts, which takes in two sequences. The first sequence is tags, and the second is the corresponding word. For example, here, this is the way it's going to be taking in sequences. The first sequence will be these tags here, noun, noun, verb, verb, and so on. The second will be the words. And this will help us count which word belongs to which class a lot more. So if you can see, if I run this to 80, I'll be able to see that some words are in different tags sometimes. So for example, if printing has been used as a verb here, and maybe printing was used as a noun somewhere here, the count of both printing as a noun and a verb will become 1 and 1. So essentially, we're trying to build the table that we had seen earlier. How we do this is run through the sequences and run through the tags individually. And once we do that, we'll see that if a tag belongs to a particular word, we will increase the count for that. Otherwise, we'll keep that count to 1 and keep moving forward. So we'll use the pair counts function, and you can deep dive into this once I send the code across to you. And what we're essentially doing, as I mentioned before, is if the word time is tagged as a noun, this is what a dictionary will give us as an output. Which means the tag noun with the word time is used 1, 2, 4, 4 times is what we need to see. So the table that we created earlier with the row and column, the row being the word or the row being the part of speech and the column being the word, and the number being the intersection of these two in the table. So once we run this sentence, we try to see if, and we're trying to map if the maximum noun counts belong to the word time, because we know in this corpus, time is expected to be the most common noun. So this is how we're checking our emission counts. You can try to run this particular line of code individually, and you'll see that these are all the emission counts for noun. These are all of the nouns that we have and how many times they've been used. So once we get the maximum of this, we'll be able to see which one or which noun is the maximum used. Now, let's try to use the pair counts function again to implement a most frequent class tagger. So what we'll do here is we'll create a fake state, which will be a name tuple, and the name of it being fake state. And this is basically just a dummy state that we're creating. So you don't need to look at a lot of stuff in this space. And we use the pair counts function again on our entire training set and our labels for the training set. So initially, we only saw them for 1 second. Yep. Initially, what we did here is something that we'll be replicating down here. Once we get the word counts, we will create an MFC table, which is called the most frequent class table, which the table will basically give us if we type a noun here or if we type time here, it should show us that time belongs to noun most. And once we run this, you'll see what the function is doing is it goes through each word in the training set vocabulary. It sees what word count for that word has the maximum tag, and it puts that tag for that word in the MFC table. So let's try to run this and see what we're talking about. One sec. I think I just need to remove these assertions for now. So once I create the MFC table, you can go through the MFC table in this way. And this is the table that we're trying to create. So for each word, as you see, we went through each of the words in the training data set. We used the pair counts function initially to see which word has the highest count pair. And then we tagged those words in our training data. So we see, for example, creek turn has been used as a noun most times in our data. So if ever it comes in our data in the future, it'll be tagged as a noun. If vagueness comes, it's tagged as a noun, and so on and so forth. So now we've created an MFC tagger and we've stored it into MFC underscore model. Now let's try to make predictions using this MFC tagger. Also, a very important thing to note is how we're replacing the unknowns. As we'd spoken of before, we have about 6,000 unknown words in our training and in our testing set. So how we're doing that is we use the UNK, or in this case, you can use NAN or UNK or whichever. So if the word is in the training data set, then we'll give that same word as an output. If it's unknown, then we'll give an NAN. Here, let's try to go over, say, 3 random keys in our data. And what we're doing here is basically we're going to break down each sentence based on the key that we take out. So for example, this is our sentence key. And you can try to copy this sentence key and go up to where we actually had sentence keys. And you'll see this is the sentence that we have. And these are the words that belong to that sentence. Now, we'll be decoding these sequences with the MFC tagger. So now that we had those sentences and we have the most frequent class tagging in this table, we'll try to run this. And we can run this on, say, maybe 5 sentences to see that each sentence key will have some words broken down. And basically all we're trying to do is predict those labels based on the words that come into us. And you'll see here, you have the predicted labels and the actual labels both for each sentence, which means if we try to match these 2 rows or we try to match these 2 arrays, it should also be able to give us a great accuracy number for our most frequent class tagger. And it usually has extremely high accuracies, the MFC tagger. So now we've written an accuracy function, as you can see here. What it's basically doing is taking in 2 inputs, except for the model, of course. The 2 inputs that it's training is the first one is the array of words, and the second is the tags that it belongs to. So C spot run, and Y should be basically something of a similar sort, right? C spots run XYZ, so on. So now what we'll do is we'll compare these tags and we will sum up the tags here. So if C spot run all match, then this is what we're trying to do is we're trying to check each word with each word. And if this comes as 1, 1, 1 here, and we sum them up, this entire correct metric goes up by 1. And so on and so forth. So if these 2 arrays match, then our prediction is correct. If these 2 arrays don't match, then our predictions are incorrect. And the number of correct ones that we get will be divided by the total number of predictions that we made to get our accuracy. So we'll try to run this accuracy and see what we get on our training and testing sets. So our training accuracy for our MSC model is 95.7 and our testing accuracy is 92.93, as we can see here. Our accuracies will obviously be higher on the training set because we do not account for unknown words in this, but the testing one does. And so the accuracy drops a slight bit. Now we'll use a similar approach to build a hidden Markov model tagger. And we'll go over the same methods that we did in the presentation. We'll first try with unigrams and then bigrams, and then we'll move on. So what a unigram count should be doing is, as we've seen before, a unigram counts will be how many times a word occurs in a sentence. And I think that's the most basic way of explaining how unigram would be. If we try to run this sentence, we see that the unigram counts function has worked out well for us, because what we're doing is we take all of the labels from the training set and we just count the number of observations in this. So for each label, we add a value if it comes into our sentence. This is something that we built in our earlier presentation when a noun was mentioned once, and if you remember the sentence, that had Mary will see Jane, and so on and so forth. So this is what we're doing in the unigram space of things. I will be sharing this notebook with everyone at the end of the session, the notebook and the presentation both. So it'll be easy for you to walk through the code line by line, which is why I'm just giving you an overview of how we're trying to solve similar things that we did in the presentation. Awesome. So, yeah, I think I'll just walk you through the structure of what's left. And you can figure out, you can run the code yourself. So here we'll be running the bigram counts and the same table that we had made earlier. We have the sequence starting, the starting and the ending tags, which we'll be adding to our sentences. And this is a place where once you have the notebook, you can create a hidden Markov model. And a model.bake will finalize the topology for you. What you're ideally doing in hidden Markov model is basically for each tag, you're adding a transition and you're adding the emission probabilities. So every time you walk through the transition and emission, the model will multiply all of those probabilities to give you each sentence. And the accuracies, as we see, on the HMM are a lot higher than the baseline tagger. And once you walk through the code, you'll be able to have a better understanding of how the HMM is functioning in code. And I think since we're down to the last 9 minutes of the presentation, we can start with the question answers. So I would encourage all of the question answers to try to be around the theory of the HMM tagger, because all of the code you will get with yourself anyway, and code is extremely accessible and you can walk through how and what is happening in the code. So if you have any doubts on how the hidden Markov model is functioning, I can jump back to my presentation and try to explain this to you quicker. Yep, so please feel free to drop your questions in the chat. I will take them up now. Awesome. Overall probability of the sentence using transition and emission probabilities. Awesome. So I'll start with, say, for example, you have a sentence that you're trying to tag, which is Spot will see Mary. And Spot will see Mary is a tag here. Start, noun, modal, verb, noun, and end. So once you have the start tag here, you will go back to your Markov model. And you see, you have a start tag, and you find the word spot. There are two places you can find the word spot. The first is here, and the second is here. So which tag do you use? If you have the transition probability of start to noun, and the probability of spot being a noun, you first multiply spot being a noun is 2 by 9, and start to noun is a 3 by 4. So if you multiply 2 by 9 into 3 by 4, you get a certain number. And for spot being a verb, you will have to go through 1, 2, 3 edges, and then go into the emission probabilities of a verb. So ideally, off the top of your head, you can see that spot will be more likely a noun, because since we're multiplying numbers that are less than 0, the more we multiply and the longer we go in the chain, the lesser the probability becomes. So once we have spot, the second is will. We are currently at the noun state. So will being a noun will have no transition probability in this case, but it'll be a noun to a noun, which is a 1 by 9. A 1 by 9 multiplied by a will being a noun is 1 by 9 again. So 1 by 9 into 1 by 9 should give you 1 by 81, which is an extremely small tag. On the other hand, if we see a noun to modal, a noun to modal is a 1 by 3 versus will being a modal is 3 by 4. So 1 by 3 into 3 by 4 gives you a 1 by 4. And you will naturally see that will has a higher chance of being a modal, because if we try to see a noun to noun transition and then multiply the emission probabilities of will being a noun, we get a 1 by 81, which is extremely low. In the case of a noun being followed by a modal and then will being a modal is a 1 by 4. So this is a smaller, walking through how we can get these tags. I've shown you till half the sentence, but I hope you understand how we're moving through these probabilities to be able to see which one is a larger probability for us to take. So spot, and in this case, will cannot be a noun because we're getting a 1 by 81 for a noun and a 1 by 4 for a modal. So this is one way of interpreting the sentence. I hope that answers it briefly. Can you explain emission probabilities again? Yeah. Emission probabilities are basically what transition probabilities in this model are you moving from the start to noun. Emission probabilities are the probabilities of a word being a noun. So in this case, you see, the 4 sentences that we had, Mary is 4 times likely to be a noun, Jane is twice a noun, Will is once a noun, and Spot is twice a noun. Once we see 4 plus 2 plus 1 plus 2 gives us 9, and we divide this entire column by 9, we get that the probability of nouns, and Mary being a noun, is 4 out of 9 observations. And that is the emission probability. So once you're at that node, what is the probability of that word belonging to that node as well? And that is emission. But moving from one state to the other is transition. So I hope that answers both transition and emission probabilities questions. And just a sec. Yeah. Which is more efficient, RNN or HMV based on time complexity? I would say if you're only basing it on time complexity, the hidden Markov model will be a lot faster. And it also, I think this kind of what is the use of that number after multiplying emission? And I will just get back to that question. But in the space of comparing RNNs or HMVs, this question is actually, if you're only talking in the algorithm space of things, I would say that the HMVs could be a lot faster. But again, this is a very subjective question, because if you have a large data set, then your hidden Markov states can be thousands and thousands of states. And even RNN can have a lot of those states. So I think this is subjective based on the kind of data that you have and the size of your data. But off the top of my head, a hidden Markov model will be slightly faster than RNN if we I use them in both similar contexts and similar data sizes. What is the use of that number after multiplying the emission and transmission? What is the role of that number? So that role of that number, so once you say, for example, I have, and I'll go back to this slide. I have one number that I get for Mary, which is from start to noun, and emission, start to noun, I will get a transition probability. And noun being a Mary being a noun will be an emission probability. Once I multiply these two, I get one number here. Once I multiply the forward transition states with will, I get another number. And in this case, if I transition through 3 states, I will get 3 broader numbers. And once I multiply all of these 3 numbers, I will get one number, which will be the probability of that one particular string being generated with those tags. And in this way, you see, we can generate a lot of sentences with a lot of different tags. I can also write Mary will. And they can all be a sentence, but they'll all be nouns, which means that the probability of that entire sentence being generated will be extremely low. And the hidden Markov model will multiply transition and emission probabilities all of the times it jumps through states and jumps through emissions. And you have one end probability for each sentence. And the maximum probability sentence will be the one that has maximum likelihood of being generated with those particular tags. So I think we're also at the end of the session. So if there's anything else in particular that you would like to know about hidden Markov models and any other probabilities, I will share these things with you, and feel free to get in touch and also drop your questions to me in private or any other place that you would want to ask them. And I'll let Vijay take over from here.
Thanks, Shantanu. The session was really good, and I hope all the learners would have learned something new from this. Thank you guys for taking out time on a Sunday, to join this session and make it a success.
Thanks a lot, guys.
Log on to GreyAtom's learning platform to unlock more free content. Subscribe to our channel and hit the bell icon for regular updates.